Back. This is week 2, and we're going to continue with divide and conquer algorithms today. But before we do that, I thought I would take a moment because your assignment 1 is due tonight, and make sure that everybody understands what. Hopefully, you're done with everything already, and you're good to go, and you've started on assignment 2. If that's not the case, that's fine. You still have until midnight to turn everything in. That was corrected. The most challenging thing that seems to continue to be Boggle. So again, I wanted to give a little bit of a more review or hint as to how to think, recursively, how to think inductively about this. Remember, with Boggle, you have a 4x4 square of letters, and I'll just go ahead and go with A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, right? And again, you are starting at a particular, you're going to have to consider all possibilities. What if I started at A? Or what if I started at L? Or what if I started at J, right? So you're going to have to take care of all 16 of those possibilities. And then, of course, you're going to traverse around this. If you start at A and you have a couple of choices, you could go over to B, you could go over to E, you could go over to F, but you can't, of course, go off the board. It's not like a cyclic board here. So what I want to do is I want to think inductively. That was the base case. That's where you start off, right? You start at A, or you start at F, or you start at L, ... right? Now what we're going to do is we're going to jump into the middle of the algorithm. I'm at a cell identified, say, by IJ, right? This is the easiest way of thinking about it. If you think about this as a two-dimensional array of characters, index 0, 1, 2, 3, 0, 1, 2, 3. So obviously when you start at A, you're starting at I and J being 0, 0. When you start at K, that's 2, 2. When you're starting at M, that's 3, 0, right? It doesn't matter if you think about it in row major form, column major form. It doesn't matter because you can always twist that game board around, okay? Remember, we are on Piazza, and I am monitoring the feed on YouTube. So if you have any questions, please go ahead and post there. But anyway, coming back, think inductively. Think more generally that you've jumped into the middle of the algorithm somewhere. This is the current cell. You got here somehow, right? You came from a bunch of other cells, and then eventually you arrived here. And you want to, well, first of all, you take the letter in this cell and you form a new word, because this other word has come along and you've got characters C1, C2, ... CK, say. And then whatever character this is, you append it to the end, and then you say, is that a word or not? By checking it against your dictionary. Hopefully you're doing that efficiently as well. I won't cover how to do that because that's just file IO and basic searching and sorting. Do not use linear search. Do not roll your own searching algorithms. Depending on the type of language that you're using, use binary search, or if it's a list, use hash-based data structure. For example, if most of you are using Python, just use a set. And then use the syntax, the in syntax, to determine whether or not an element is in that set. And that's a amortized constant time algorithm, right? Rather than searching over 300,000 letters or words in your dictionary over and over again. Okay. But anyway, once you've checked whether or not this is a word, throw that into your bag. You're going to save that and print it out later in a nicely formatted manner, whatever, right? But otherwise, now we need to make sure that we're making progress. And so what do we do next? Right? Let me go ahead and rewrite this. I'm at, again, cell IJ. We could go up. We could go right. We could go up and right diagonally, right? But also remember that you have, 8 total possibilities. You can go up to the left, left, down to the left, down, and down and to the right. You have 8 possibilities surrounding this cell, potential possibilities surrounding this cell. So how do you do that? Well, you just think of it as an offset. If I were to go left, right, then again, if you're thinking of this in column major form or row major form, it doesn't matter. But I'll think about it in terms of Cartesian values, right? So if I is expressing x and I go left, then this is I minus 1. And I'm in the same row here, so it's going to end up being j. If I go up, right? If this is a Cartesian product, plane, then I'm going to be going in the up direction. I increment y, right? So this is going to be I and j plus 1, right? And then, of course, you can set up a series of loops to try to enumerate each one of these possibilities. 1, 2, 3, 4, 5, 6, 7, 8. One possibility, however, is what if there's none? What if you stay there? You don't want to stay there. If I stay ij to ij, right, that's not making any progress. And it's repeating a letter. You can't repeat the same letter over and over and over again. You need to go to other letters. There may be duplicate letters. For example, if I had 2 E's over here instead, then so be it. I can have words with 2 E's, B-E-E. Nice little B there, right? But I can't use the same letter over and over and over and over again. That's not allowed. That's not part of the game, okay? So you can hard code, of course, these 8 directions, all right? Or you can, set up a clever loop to go over all 8 of those possibilities, all right? But there are some things that you have to keep in mind, right? One is that you can't go off the board, right? So if you've already computed your I and j, and the next one that you want to go to is, say, I prime and j prime, right? Right? If either one of these falls off the edge of the game board, right? If it's less than 0, then no, you can't go there. Right? If it falls off the game board the other way, right? If it exceeds 3, then no, you can't do that. In fact, this is not an X. This is a no, you can't do that, right? So then you don't do it. You don't recurse onto that cell. You skip it, right? But there's another possibility here of things that you need to cut down on. Again, you don't want to repeat the same letter over and over and over again. So if I go from ij to I prime j prime, but I j prime j prime is already used, or what I've been calling it is visited, because this is basically a graph. It's a grid graph that you're kind of a grid graph that you're iterating over, but where you can just go up, down, left, right, or diagonally in any of those cases. Then do not go, right? And I'll use the same color here. You can't do that. Right? Don't repeat that letter again. That means that you're going to have to keep track of this. You must keep track of where you've been. And the easiest way to do that is to simply maintain another 4x4 grid, right? That has flag values, right? If I'm just going to use my highlighter here. If I start at A and then I go over to B, right? And then I go down to E, and then I go over to K, right? Then I need to make sure that I know that when I'm at K here and I'm thinking about it inductively, recursively, that I don't go back to what I've already visited. Or that if I eventually come back up here to C, I don't go back to B. Right? Coloring it a color, or setting a flag value is visited or something like that, that's going to be the easiest way to do that. You just have to be careful that when you backtrack in your algorithm, you make sure to undo that coloring. Unfortunately, there's no easy way for me to do that. There's no clear highlighter, but you get the. Hopefully, you'll get the idea here that when I backtrack, right, I uncolor or mark K as unvisited, so that when I go over here, I can visit K again, right? Because that's enumerating all possibilities. So my other tips are going to be, one, make sure that you are testing against a reasonably large database or a reasonably large dictionary. If you want to download the one that we're going to use on the CSE server, great. Otherwise, troubleshoot with a small one. Keep a counter and troubleshoot, and make sure that you're visiting every single cell. Make sure that you are enumerating those 12 million possibilities. That number is in the handout with your recursion. If you are not, or if you're exceeding that, then that is a huge red flag that you need to go back and rethink what you're doing. All right. So hopefully that was enough to get to continue. Hopefully you've gotten a good start on it already since it's due today. But hopefully that's enough to clear anything up that you might need. Right? You do have to keep track of all of those possibilities. All right. Still no questions online. So what I want to do is I want to go back to what we were working on Friday, which is repeated squaring. And again, the task here is that you want to compute a to the n mod m for a very, very large n, right? A and m could be very large as well, but that's not really what we're focusing on here. The naive approach that I programmed here last time with this very, very large number that I just keyboard mashed, I let this run for 20 minutes at the end of the presentation on Friday, and it still wasn't there. In fact, this would take probably maybe even centuries to compute, especially in Python here, for this actually to execute with this naive algorithm of simply just going a times a times a times a times a, which is what we're doing here. A times a times a times a. We're, of course, modding out on each iteration. So the naive approach of making n-1 multiplications leads to an exponential inefficiency. What we left off with last time on Friday was the following pseudocode. Right? This pseudocode, we developed this pseudocode, and I demonstrated what this was doing. But just as a review, let's go ahead and go through it again to make sure that we understand what we're doing here. So first of all, the term, this line, and this line down here. What are we doing? We initialize it to, in this case, alpha. I'll just go ahead and write it as a here. Right? And then on each iteration of this for loop here, what we're doing is we're squaring it. So a becomes a squared. A squared, when you square that, becomes a to the 4th. When you square that, a to the 8th. In other words, we're able to jump up by an exponential amount each time with just one multiplication. 1, 2, 3 multiplications here total. And we can go up another power of 2 with just one more multiplication. Right? That's repeated squaring, and this is called binary exponentiation because we're using the binary representation of n here. So why does that help us? It helps us to do this faster because what we're going to do is we're going to use the binary representation of n and only take terms that matter. Remember, think about, I think that the example we used was a to the 77. That can be broken down into a to the 64th times a to the 8th times a to the 4th times a to the 1st. Each one of these exponents that I just wrote was a mere power of 2. Now, there were lots that we skipped, right? There was A32, A16. We end up computing those in this line right here, but we end up not using them, right? Why? Because ultimately, that bit is going to be 0 in the representation of n, right? We also skipped, we computed, but we didn't use a to the second power here. So all we have to do is compute powers. And once we've got the powers, we only use the ones that matter according to the binary representation of n. And that's what this line here is doing. If the bit is 1, then we multiply product by the term, modding out m to continue. So when it's 1, all right, we get a1. When it's the second one, let me go ahead and write this down actually. That 77 in base 2 is going to end up being 1, 0, 0, 1, 1, 0, 1. Right? We work from right to left, and when the bit string is 1, then we know that we need to include that in our in our running product, right? The first bit string actually is taken care of outside here. If it doesn't include the power a to the first, well, if the first bit, the lowest order bit here is 1, then yes, we initialize our product to 1. Otherwise, we initialize it to 1, right? Now, of course, you can take out the possibility that alpha here is 0. If it's 0, just stop and immediately return, right? Return 0. So let's go ahead and run through this algorithm with an actual specific example. And for that, I'm just going to use the one from the book or from the lecture notes here that we're going to want to compute 12 raised to the power 26 mod 9. Right? So n is 26. And what I want to do is I want to compute the binary representation of this number. That's going to be 1, 1, 0, 1, 0. Right? And just to verify really quick, this is going to be 2. 4 is not included, so 2, 8, and 16. 2, 8, and 16, when you add those numbers up, you get 26. Yep. All right. So let's run through this algorithm. Let's with actual values here. So actually, let me give myself some more room here. 1, 1, 0, 1, 0. There we go. And that's our n. Let's go ahead and look at I, which is going to be our iterator variable here. J. And what else do we want? We also want term and the end and the product, right, that we're going to compute here throughout this thing. Remember that we start at the lowest order bit. So this initialization here, it's 0, and so we end up with a product of 1. Right? Term here has already been, sorry, we should have started at the top here. Line 1, we initialize term to A. A in this case, again, is 12. So term gets a value of 12. And this is before we even start that first iteration of the for loop. So there's the initialization. Now we go into this for loop for I running from 1 up to k, where k is the number of bits in this. So I is going to be 1, 2, 3, 4. Right? How does term and how does product change? Well, first of all, term is going to be squared and then modded out by 9. Right? That's unconditional for the for every single iteration of this for loop here. So a squared becomes 144. But remember, we're modding out each time. We're modding it out to keep it small. Mod 9. All right. What I'm going to do is I'm going to cheat and I'm going to use Wolfram Alpha. And or you can cheat as well with and pull out your TI-82 calculators or whatever. And 144 mod 9 is going to have a remainder of 0. Oops. Is that right? That's not. Oh, you know what? It will, but that's not from the handout. So sorry. Let me go ahead and back up. Oh, we can go. We can continue. We'll persist in this. Unfortunately, this is not going to be all that interesting because term is going to end up being 0, in which case we're done. So no, I don't want to do this. So here's the original. Sorry. 17 mod 17. There we go. Okay. So 144 mod 17 is going to have a remainder of 12. There we go. Now, just because we repeated here doesn't mean we're going to repeat in the same thing over and over again. Actually, no. Sorry, it's 8. What am I saying? 144 mod 17. Bear with me. Yep, it's 8. Right? I just did that in my head, and I didn't get it right the first time. So 8. Otherwise, it would have if the term never changes here Squaring it gives you the same result after the modulus. Then you can write it throughout the same throughout the entire algorithm here. All right. So we check the bit string, right? The bit string here in this case is 1, and so we end up with product times term mod m. So the product is currently has a value of 1. Oops. Times the term 8 mod 17. Well, that's convenient. We don't have to really go to Wolfram Alpha here. That's going to be 8. Right. Okay. Next iteration. Now I'm looking at the iteration for I is 2. I square the term, so 8 times 8, 64, oops, mod 17 is going to give me 13, a remainder of 13. 17 goes into 64 3 times evenly with a, right? 3 times, 3 times evenly, but then it has a remainder of 13. Right? We look at the bit string here, and its bit is 0. In other words, it does not contribute, and we simply just copy over this value over here because it doesn't change. Product, this if statement here will not execute it, and therefore it stays the same. Right? Next iteration, we square the term again. 13 times 13 mod 17. That's 169 mod 17, which I believe is going to have a remainder of 16. Yep, good. I just counted backwards. 170 would be the next power, or would be the next multiple of 17, and so it would only go into it 9 times with a remainder of 16. The bit string here does have a 1, so we do end up being true on line 8, and we multiply through. This one's going to be a little bit more difficult to do in my head. 8 times 16 mod 17. And for that, I'm just going to go to Wolfram Alpha. 8 times 16 mod 17 is going to end up being 9. Yep, good. Next iteration, we square the term unconditionally. So 16 squared mod 17. And without beleaguering the point, that's just going to be 1. That's a remainder of 1. And so really easy here. 1, again, the bit string here is 1, so we do include that factor in our exponentiation. 1 times 9 mod 17 ends up giving us 9. Right? And you can verify that 12 to the 26 mod 17 is indeed 9. That's our last final product. Again, you are not going to be allowed, when you program this, you are not going to be allowed to use any built-in functions in your in whatever language you're using. You can use them to verify that your answer is correct in your testing and troubleshooting, but your actual implementation will have to be this binary exponentiation, this repeated squaring. Right? So to help you with that a little bit, what I want to do is I want to go over here to my Python script, my Python demo. Again, this is bad. We're not going to run this again. So let me go ahead and get rid of all of it. There we go. All right. So you might ask an easy Google search, if you look it up, would be how do you convert a number to binary? It's kind of a weird question because it's a computer. Everything's already binary. So what you actually want is a binary representation. And a binary representation is usually done as a string. So, for example, if in Python to do this, you can use printf style formatting if you want, but otherwise there is a free format method, I think. So if I've got a value x here, let me go with n, right? And I'll illustrate this with 77, the value that we did before. Then the binary representation, I'll call this a string, binary string of this, is going to be equal to format of n, and then you give it a lowercase b here. I'm pretty sure that if you gave it an x or an h, that would end up being hexadecimal or maybe O for octal, but B is going to be for binary. Right? And let's go ahead and print that out. Oops. There we go. And demo. There we go. And we get that same binary representation that I wrote down before. 1001101. We did 26 next. And that's the binary representation we had. Now, they're not going to be leading zeros, but you don't need it for this exercise. But of course, you can look at that binary representation, and this is how people usually do it. And then then do a string comparison. Well, is this character 0 or is this character 1? I want to show you a little bit better way of doing it using what's called bit twiddling. Right. So bit twiddling is actually, again, it's kind of a weird question to ask, can I convert an integer to binary, because it's already binary. And if you think in terms of binary on a computer, then you can do direct binary manipulations. For example, dividing something by 2, dividing 26 by 2 to get 13. What does the value 13 look like? I'm just going to cut and paste this. And let's look at what if we divided 26 by 2, what would it look like? It would look like the same number, but that last 0 is chopped off. In other words, we've taken that number and we have shifted it. That's called a right shift. And it works because it's everything in a computer is base 2. When you divide by 2, you are basically shifting it. You already understand this intuitively. When you multiply by 10, what do? Do you actually take out your TI-82 and start multiplying? Or when you divide by 10, no. That's really easy because it's base 10. You just take the decimal and you move it over, right? For one way or the other for multiplication or division by base 10. And you can do the same thing in computers. It's called a shift, right? So bit shifting. I'm going to shift it right to divide by 2. Divide by 2 by shifting to the right. Right? So my n is still 13. I've not changed that. Actually, no. Let's go ahead and go with n is equal to 26 because I want to make sure that it gives me the same value. N is equal to n, and then I'm going to shift it right by 1 bit. Right? Let's go ahead and print n, and we'll also print the binary representation of n to show you that indeed it is now 13. Right? 13, and then the same binary representation. You can shift it by shift it to the left to multiply by 2. So 26 times 2 is going to end up being 52. Right? And what we've done is we've shifted that number to the right, and we filled it in with a 0 because we've taken the decimal place and we've just simply moved it over. We have an infinite number of zeros afterwards in order to take care of that. You can do it by more than one. So if I wanted to shift 26 by 2, that's going to be division by 2 and then another division by 2. In other words, a division by 4. It's not going to look that pretty because it's I'm actually wondering what it's going to look like here. That's going to be 13. And then 13 divided by 2 is going to be 6.5, but because it's an integer, I'm hoping for truncation here and getting 6. Yeah, exactly. Right? Because all bit shifts are going to be probably integer results. Right? I think that there's also a cyclic shift. If you, at least in some languages support this. Let's see if Python supports this. I'm not sure. Nope, there is no cyclic shift in Python. But that's division by 2, division by 3, division by 8, division by 16, right? Or you can do it over and over and over again for extremely efficient division just by simply shifting the bits left or right. Another bit twiddling, twiddling the bits. Twiddling is just messing with. That's what the word means. You twiddle with it until you mess with it and manipulate it in small ways and then to get what you want. The shifting is one aspect of bit twiddling. Another one is called masking, bit masking. So to get a particular bit out of a binary representation, you can use the bit mask. All right, and this is the single ampersand. In programming languages that in Python we use and or, the keywords and or, to get conjunctions and disjunctions. Most programming languages use 2 ampersands or 2 Sheffer strokes here, right? And or. Oops, there we go. But if you use a single and, it's still a logical and, but it is a bitwise and. So let's go ahead and take A is equal to 13 and B is equal to 26. And what we're going to do is we're going to take a result of A and B. Right? There we go. And let's go ahead and convert it and print it out. Right? Print. Well, we're working with X now, so print X, format X in binary, and then print it out. Yeah, we'll be okay here. Right. All right. 8. All right. That's kind of weird. That 13 and 16 and 26 is 8. We're not adding them together. We're not subtracting them. We're not doing anything. What we're doing is we're looking at each one of the bits. 26 here is 11010. 13 is going to be that value. And so what happens when we take a bitwise and of each one of those bits? For that, let me go ahead and go back to my iPad here. There we go. So again, the binary representations of 26 and 13 are going to be 11010. Right? And 13 is going to be shifted, so it's going to be 1101. I'm going to put a padded out 0 here because remember, it didn't print out that leading 0. It never does. So what happens when we take a bitwise ampersand here? It means that we take these bits and we AND them together. False and true is true. True and false is false. Oh, what am I doing? There we go. So false, false, false. False, false, false. There we go. False, false, false. The only bit that ends up being true is this one right here. 1 and 1. That's going to end up being 1, and then this is false. So what value does that give us? This is 1, 2, 4, 8. And that's why we got 8 out of that result. And 1, 0, 0, 0 is the result that we got when we converted it to binary and printed it out. Why is that useful? Because it allows you to pull out a specific bit. If you use a particular number, then it allows you to pull out a specific bit from another binary representation without mucking around with a bunch of strings. So for example, get the lowest order bit of a number. Here's n. Right? I'll just mash the keyboard here. Right? And let's go ahead and get a binary representation of n and print it out. So this will just be the last line that we're paying attention to now. Right? That's a nice binary string, but great. I only want this bit right here. Is it 0 or is it 1? So what I can do is I can mask it, right? I can say, I want the result to be x of n and some other bit string. 1, right? 1 has a value of 0000001. In other words, it only looks at that lowest order bit. And this will give me the lowest order bit of n. So print x. Right? It'll be 1 or 0. Right? And in this case, it's 1 because that bit is 1. Let me go ahead and make this even so that that lowest order bit is instead 0. And we get 0 here. You can get different bits. So if you want the third lowest order bit, right? So not the 1's place, not the 2's place, but the 4's place, then of course all you need to do is mask it with that value, 4. Right? And that gives us this bit right here, which is 0. You don't if you have difficulty thinking in binary, that's okay. You can use binary literals in most programming languages by using 0b 100, right? And that's this 0b is just formatting it, so ignore that. But what we're doing is this is not 100, this is 100, which is 4. All right. and we get the same result as before. If you want to, if you can use it for 1, you don't need to. If you want the 16th, 32, 64th bit, 64's bit. I don't know if that's a technical term or not, but that's 0, or that's 1, 2, 4, 8, 16, 32, and then that's the bit that we want right there. And we simply mask it with another bit string. Most programming languages support these tricks. You can, of course, use an OR instead to get a bitwise logical OR. You can shift. There were a couple of other things that you can do with bit twiddling, but you can use them all in conjunction with each other to get very, very clever, very, very fast, because this is just bit manipulation. Bit manipulation is extremely efficient in most programming languages. All right. Let's see. You know what? All right, no comments or no questions so far. So let's go ahead and over here. All right. So repeated squaring. What about an analysis of this thing? All right. Again, all it does is relies on the binary representation. As we square these things, it's only one multiplication each. Is potentially an additional multiplication for the product and the value to get a running total. So at most, there are going to be 2 multiplications on each one of those for loops, if you want to think about it as an upper bound. But it entirely depends on the binary representation. So if I gave you an n, how many bits are required to represent n? Well, that's going to be log n, basically, right? And n is the actual true input size. So, i.e., this algorithm is not logarithmic. It's going to be linear with respect to n. Okay. Where n is the number, n is not the input. Remember, that's why I give you the 5-step process of identify the input and then identify the input size. In this case, the input is little n. The input size is not little n, right? Because that would mean like if you had an input of 2 billion, are you writing down a billion tick marks? No, you're writing it in a compact binary representation. And to do that, the number of bits required to represent a number is log base 2 of n. Just like the number of digits required to represent a number is log base 10 of n, right? And n here, big N, is what we're using as our true input size. That's why it's that 5-step process is so important. At least I think it's so important, is because you can't confuse the input for the input size. Otherwise, that naive way of doing it that I've erased now, it would look like it's linear because you're doing n minus 1 out multiplications. But n, little n here, is not the input size. It is the input. The input size is log of n. Okay. All right, still no questions. So let's take a look at another divide and conquer approach. And we're also going to be doing more multiplications and stuff, more math stuff. How can we improve our math? Karatsuba multiplication. All right. So the multiplication that you've done in grade school is highly, highly inefficient. That's why I think in grade school they make them multiply 4-digit numbers at most, and then they say, okay, now here's a calculator, go to, right? Let's go ahead and take a look at what that looks like, though. If I had 2 4-digit numbers and I went with the grade school method, 3, 4, 7, 2 times 4, 8, 9, 7, how many multiplications would I end up needing to do? Now, in grade school, what you did is you took the first digit here and you multiplied it with the second, the third, the fourth, the fifth, right? So you ended up with a number of, and then of course you had to carry things through. 49, carry the 5, 7 times 4, 28, 3, carry the 2, 7 times 3 is going to be 21, carry the 2, so 2, 3, right? Something like this. Now, when you multiply the next number, 9, with 2, 7, 4, and 3, you had to be careful to shift it over. Sometimes people write explicitly the 0. Sometimes they just leave it blank. Right? So 9 times 2, that's 8. Carry the 1. 9 times 7, 63. 64 with the 1. Carry the 6. 9 times 4, 36. 42. Carry the 4. 9 times 3 is going to be 27. 32, 31, etc. Right? So there's a blank there, there's a blank there, and then in the last one there's going to be blank blank. How many actual multiplications did I end up doing? I did 4 here. I'm not going to do the full thing. I did 4 multiplications here, 4 here. Right? This shifting, as we've already observed, is not a multiplication. It doesn't cost you anything to take that decimal place and move it left or move it right. If you're multiplying by 10, because this is base 10 here, that's free. All right, that's not a multiplication. That's not an addition. That's just moving the digit. It's moving a bunch of bits, or in this case, digits, left or right. For the third number, we would need 4 and then another 4. So in other words, 16 multiplications to multiply a 4-digit number by a 4-digit number. All right. So if we were to generalize this, the naive approach, if we had to multiply 2n-digit, and I'm going to emphasize that we're talking base 10 for now, digit numbers requires, hopefully you guessed it here, it's going to be n squared, single digit multiplications for the old grade school method. Okay. Is there a better way? Can we improve on this? Right. Just a sec. Still no questions. All right. We've got oh wow, only seven folks have joined us today. That might unfortunately mean that people are working on their homework. Hopefully they watch this again though, right? All right. So what I want to do is I want to show you some magic tricks. Okay. So let's go ahead and try with 47 times 52. Right. Now that's two-digit numbers, so it would require, say, 2 squared is going to be 4 multiplications. But what we can do is we can start breaking this thing up. So 4 times, and then this is just going to be in scientific notation here, 10 to the first power plus 7 times 10 to the 0th power. That's 47. And I just split it up into 2 one-digit numbers that are shifted by 10 or not shifted at all. Okay. Now multiply that by 52, which can be broken up as 10 to the first plus 2 times 10 to the 0. Okay. Now think about this in terms of A, B, C, D. A, B, C, D. Don't worry about the powers of 2 or the shifting. This is A plus B, C plus D, and we multiply this together. Just think about those letters. And, hey, we can go ahead and bring the FOIL rules to bear. If you're not familiar with that acronym, that's first, outer, inner, last. The first is going to be A times C. The outer is going to be A times D. Those are the two outer values. The inner is B and C, and then the last is going to be B and D. So in other words, it's equal to AC plus AD plus BC plus BD. Right? We all learned that in grade school, right? Just like we learned the grade school multiplication. That's still going to be 1, 2, 3, 4 multiplications. Again, the multiplication by a power of 10 is not going to matter. Let's go ahead and write it out though. That's going to be 4 times 10 to the first times 5, so that's going to end up being 10 squared. Right? Again, the square doesn't matter. We're not actually multiplying by 10. We are shifting things. Plus 4 times 2 times 10 to the first, right? Plus, and now I'm an I, so 7 times 5 times 10 to the first, plus 7 times 2, 10 to the 0, right? Unfortunately, that's still 1, 2, 3, 4 multiplications, right? But let's observe this thing over here really quick. How did I get that? Right. Well, first of all, let me go ahead and write down this number up here again. Remember, let me give myself some room over here. A plus B, here's the magic. C plus D is equal to this thing over here. In fact, I'm not going to even rewrite it. I'm going to use my magic here. Copy, paste. There we go. All right. Now let's manipulate this. I'm interested in this inner part right here. This AD plus BC. This part right here. Right? What I'm going to do is I'm going to magically take 2 multiplications and make them into 1 multiplication. Right? The way that I'm going to do that is by simply collecting terms. I'm going to AD here, ADBC is right here. I'm going to take this term and move it over here, and I'm going to take this term and move it over here. So what do I have then? A plus B, C plus D, subtraction of AC, subtraction of BD gives me AD plus BC. Right? That value there can be replaced with this thing over here. Now you might be asking yourself, wait a second, you just said that you were going to take 2 multiplications, 1, 2 multiplication, and reduce it down to 1 multiplication. I don't see that. I see 1, 2, 3 multiplications. So you've actually taken 2 multiplications and blown it up to 3. Here's the magic. The magic is that we've already computed AC and BD. Right? All we have to do is reuse them. Right? So the magic being that I can take 1, 2, 3, 4 multiplications of single-digit numbers here, and I can get by with 1, 2 multiplications, and A, B, C, D. Again, they're just single-digit numbers in this case. If I just add them together, then I can get by with 1 additional multiplication. So in other words, what I can do here is I can take something that required, what was it before? I don't even know how many, something like 4 multiplications and X additions. And I can translate that into 3 multiplications with 2 additional, however many additions there were before. We might actually be cutting that down on that too. That doesn't matter because I'm going to focus on multiplications here. Multiplications are far more expensive than additions in any hardware. Because additions are just, or multiplications are just iterated addition, plus addition of 2 additions. Right? Might not seem like a huge deal, but if we can repeat this process in a divide and conquer kind of strategy, then we might be able to speed up multiplication. Again, it's n squared for the naive approach. If I can cut it down to 3 multiplications and repeat that, then I might be able to improve this. So here's the scenario. Given 2n digit or bit, whatever, it doesn't matter, digit numbers. We're going to, 1, split them into 4 n divided by 2 digit numbers. Right? I'll call them A and B. I'm going to split A into A naught is what I usually use. Is that right? No, sorry, A1 times 10 to the n divided by 2 plus A naught. This is a generalization of what we did over here, right? Where I took powers of 10 over here. Well, now I'm taking a power of 10, but I'm dividing it by 2, right? This is if I view A as this number, what I'm doing is I'm taking A1 and A2, A naught. I'm taking half the digits, the upper half, the most significant digits, and I'm taking the lower half, the least significant digits here, and I'm splitting them up into A1 and A2. B1 times 10 to the n divided by 2 plus B1, right? Oh, sorry. 0. There we go. Then 2. What we're going to do is we're going to compute A times B with the following. So A times B, I'm going to do the same split that I did before. A1 times 10 to the n divided by 2 plus A0, A naught. B1 times 10 to the n divided by 2 plus B naught. Right? And I'm going to use the FOIL rules because I've broken it up here. And I get A1, B1, 10 to the n. Remember that I'm taking n divided by 2 times 10 to the n divided by 2 times 10 to the n divided by 2. That gives me 10 to the n. All right. Plus, and then this inner part here, where I've got A1, B naught, plus A naught, and I'm just factoring out immediately here a 10 to the n divided by 2. Right. Plus the L, this is the F, this is the O, I, and finally the L of FOIL is going to end up being A naught, B naught, and then there is no, there is a 10, but it's raised to the 0 power. Right? Then I can replace this inner part here with that trick that I just did. A1, B1, 10 to the n, plus, give myself a lot of room here, A1 plus A naught, B1 plus B naught, minus A1, B1, minus A naught, B naught, there we go, times 10 to the n divided by 2, plus A naught, B naught. Hopefully I transcribed that well enough there. Observing here that A1, B1, that's one multiplication that can then be reused. B naught, A naught, B naught is another multiplication that can then be reused. So we really only have 1, 2 multiplications. So these are being reused, and then 3 multiplications here. Now, this kind of looks like the original up here, that if I just, if I just take it, that kind of looks like that's just A times B again. No, it's not. It's 2 digits that are half as big or half as many digits as before. This A1 plus A naught, that is a digit. That is a number that is n divided by 2 digits. This is an n divided by 2 digit number, and so multiplying them together only gives me 1 additional multiplication. Right? Cool. Repeat that until you get down to the base case. The base case being when you've got, well, not this base case, but when you've got a single digit number, 2-digit. You can't take a single digit number and split it up into any more any smaller digits. So just go ahead and multiply them together. Right? That's the base case. So is this an improvement? Is this better? Right? So what I'm going to do is I'm going to set up a recurrence. Here's some review from say 156. I want to I want to quantify the number of multiplications. So set up a function for that. M sub n is going to be the number of multiplications by Karatsuba on 2 digits of size n, right? N digits on 2 numbers. Sorry, let's rephrase that. 2 n digit numbers. There we go. Okay. So you can set up a base case here that if it's a single digit number, then it's just going to be 1 multiplication. 5 times 7 is 35, right? But now what we need to do is we need to set this up as a recurrence, right? I split it up into 4 n divided by 2-digit numbers. And then I handed that off, and I don't know how to do this multiplication. So I'm going to recursively do this, and okay, here's a 16-digit number. All right, split it up into a bunch of 8-digit numbers, and then make a recursive call to this function or this method that you are that you're implementing, and the input is only half as big as before, right? So it's the number of multiplications required for that first one, but that's the input has been cut in half, right? This is the first multiplication, 1. Second multiplication, third multiplication. And that's just going to be simply m n divided by 2 plus m n divided by 2 plus... Is there any non-recursive cost here? There is, in that you have to add these things together, but we're not quantifying. We're not trying to analyze this with respect to additions. There's no multiplication here that is done non-recursively. So our non-recursive cost here is 0. This is the recursive cost. This is the non-recursive cost. And all we have to do is observe that there are 3 of those terms, and that's n divided by 2. Right? 3 multiplications on numbers that are half as big as the input. We're ignoring the fact that there are 2 inputs, A and B, each time, because we want to simplify it. Besides, the size of the input would only be 2n then, in which case, that's a constant that you ignore eventually. Right? So how do we go about solving this? In other words, this is going m sub n. I want to know, is this big O of what? Right? If it's less than n squared, if it's n squared, then it's not an improvement. Is it less than n squared? It's supposed to be a question mark there, right? To answer that, we need to bring another tool to bear. And here is a reminder about what that tool is. Right? Here's the Master Theorem. Right? If you have a recurrence of the following form being you've got a recurrence, and you are making a recursive calls. A recursive calls. Right? On input that is cut by a factor of b, right? That's where this b comes in over here, right? That you're making a certain number of recursive calls on an input that, if b is 2, then it's half as big. If b is 3, then it's 1/3 as big. If b is 4, then it's 1/4 as big. And then you've got some non-recursive cost here, right? So f of n is some non-recursive cost. Then once you've then if f of n is some order, or is there we go. F of n is order. Actually, I don't need to write this. It's right here. F of n is some order, is bounded by a polynomial of degree d. Then that gives you a, b, and d. And all you have to do with those 3 values is plug and chug. Right? If a is strictly less than b to the d, then you've got a recurrence with this asymptotic analysis. If they're equal, then you've got a recurrence of this asymptotic analysis, and if it's greater, then you've got this. Again, what this is doing is it's kind of capturing the notion that you are doing less recursion than you are doing non-recursive work. In the third case, you are doing more in your recursion than you are doing non-recursive work. If you are this equals here, the intuitive notion there is that you're doing roughly the same amount of work in your recursion as you are non-recursively. But in any case, all 3 of those that if you've got a recurrence of that form, you can always apply the Master Theorem, and then you don't have to do any work. You don't have to solve that recurrence. What does it look like over here for ours? So let's go through that process. A here is 3 because I'm making 3 recursive calls. B, I'm cutting the input in half each and every single time. But what about D? D here, there's no non-recursive work. That's still bounded by a polynomial. It's still bounded by a polynomial of degree 0. because that's order 1. You're doing a constant amount of work. 0 is a constant, right? So my D here is going to be 0. Now all I need to do is plug and chug into the master theorem. So we've got 3 versus 2 to the 0. Well, 3, hopefully you understand that 3 exceeds that. And so I'm looking at case 3 of the master theorem. By case 3 of the master theorem, we know that's n to the log base b of a. So this is going to end up being, I'm going to get rid of all of this. By the master theorem, we have that the number of multiplications performed by Karatsuba multiplication is going to be order n to the log base b, that's 2, of a, which is 3 in this case. You can pull out your calculators and find that this is actually going to be less than 2. Again, I'm going to go with Wolfram Alpha here. That if I've got log base 2 of 3, that's going to be about order n to the 1.584 dot 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 dot, right? And I'm putting in order here because, of course, this is an irrational number that goes along forever. If I put theta here, technically no. I could put theta up here because it's in symbolic form, but technically this should only be big O, right? If I'm writing it out as an actual number. Is that better? Right? Certainly. The exponent here is 1.584. Right? That's much better than the naive way of doing it, which is going to require n squared. So we've cut this down to n to the 1.584 dot dot dot. Right? That is a speed up. Unfortunately, for the same reason that I usually discourage the use of recursion in CS1 and 2, it doesn't really buy you all that much in practice. That it takes very, very, very large numbers to start seeing the payoff for this. Because ultimately you're paying for the recursion, you're paying for the splitting of the two inputs, you're paying for the additional additions that you have to perform, etc. So if you were to actually, plot these things, the naive solution for small inputs is still going to be faster. But there comes a certain crossover point where those two polynomials meet, and then Karatsuba multiplication starts paying for itself after that. There's just such a large constant sitting out front for most machines and for most implementations that it's just not worth it to do it in practice. And besides, there are better algorithms. There's the Tomb-Cook way of doing it, which I believe is just another algebraic trick. You split it up a different way, and then you can cut it down a little bit further. The cutting edge, of course, is to do fast Fourier transforms and discrete Fourier transforms, which is beyond the scope of this course, and we're not going to get into that, unfortunately. All right? Okay. So that is a good reminder of, let me go ahead and go back over here, of the Master Theorem. Right? And if you need that in your notes, that's going to be in the CS2 book, for 156, or you can actually go to my 156 videos, and I cover the Master Theorem and recursive analysis there. One more thing that I wanted to talk about today is the same kind of trick, but applied in an even greater scale. So matrix multiplication is also a very, very common computational operation. And if you haven't had linear algebra yet, that's fine. I don't think I forget whether I don't think I assigned this for programming this summer. But let's just go ahead and remind ourselves what we're talking about with respect to matrix multiplication. So first of all, a matrix is a table of numbers, basically, right? So instead of a single number, you can have a matrix, a 1-by-1 matrix, in which case you've got a scalar, a single number, right? But of course, you can have like 3, 4, 7, 8. This is a 2-by-2 matrix. You can have non-square matrices if you want, and matrix multiplication works for those. You just have to make sure that your dimensions in the middle match. 4, 3, 2, 1. There. So how does matrix multiplication work? You end up when you multiply an n by n matrix with another n by n matrix, you end up with an n by n matrix. In this case, it's a 2 by 2 matrix and a 2 by 2 matrix, so we're going to end up with a 2 by 2 matrix. But to get a particular entry, what you do is you take an entire row, and then you flip it, and you multiply each component by the column. So again, you take a row, you flip it vertical, and then you multiply each one of these things together. So for example, if I take 3, 4, and I flip it, and I multiply it by 4, 2, what I get is 3 times 4 plus 4 times 2. Right? 3 matches up with 4, 4 matches up with 2, and I'm left with, that's 12, 8, so that's going to be 20. Right? That's for the first entry. Now, how do you get the second entry? The second entry is going to be the first row, but the second column. So for this first row over here, you're going to end up with this first row, and then you do this column, 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 column if you had multiple columns. In this case, it's going to be 3 times 3 plus 4 times 1, which is going to be 13. Right? And what about the second row? The second row, then you get the second row over here, and then the first column, and then the second column to get these two numbers here. Right? And I don't know what it is. I just made these numbers up anyway. But you get some numbers here, x and y. Right? In general, these values can be written out. So let's go ahead and write A, B, C, D times E, F, G, H, just so that they're all distinct. And give myself plenty of room here. That's going to be AB times EG. So AE plus BG. You can have negative entries here, but you sum them up no matter what. And then the second entry there is going to be AF plus BH. Then down here on the second row, we take the second row of the first matrix and match it up with the first column. So C, E, D, G, right? And then C, F, and D, H. There we go. Right? And that's for a 2 by 2 matrix. What does it look like for with a 3 by 3 matrix? Well, you'd have 3 elements over here, 3 elements on this row, and then you'd match it with the 3 elements in this column, 3 elements, 3 elements, 3 elements, 3 elements, etc. So if we were to do this the naive way of writing it out like this, for on n, actually, let me rewrite this. To multiply 2 n by n matrices requires, naively multiply 2 n by n matrices requires how many multiplications and how many additions? So let's look at this from a general perspective here. If this is A1, A2, dot, 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 AN, and then I've got the second row, the third row, etc., etc. I'm not going to write those all out. But if I've got the first row here, and I flip it and I multiply it with the first column here, this is going to be B1, B2, B3, dot, 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 Bn. So I'm going to make the observation that for one entry, it's going to require n multiplications. Right? Why? Because A1 gets multiplied with B1, A2, B2, A3, B3, dot, 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 AN, Bn. All right? And how many additions? One entry will require n minus 1 additions. Well, why did I say minus 1? Well, if I've got n elements, if I've got 4 elements, I only need to do 1, 2, 3 additions. right? So I don't need to do n additions because I can start with that first one. If you start with 0 and then you add 1, the first, the second, third, fourth, then yeah, that's n additions, but you can get away with n minus 1 additions here. So the final observation here is the number of entries is going to be n squared, right? Because this is an n by n matrix situation. So multiplications, if each one requires n multiplications and there are n squared of them, that's n cubed multiplications. If there are n squared entries and each one requires n minus 1 additions, that's n squared times n minus 1. In either case, both of these are going to be order n cubed. Right? Now you might ask yourself, well, what about that 5-step process? What's the input? What's the input size? What about those two things right there? The input is two n by n matrices. The input size, we can kind of hand wave that and say that it's just n. Right? And granted, it's the input is this matrix right here and this matrix right here. Oops. Which is going to be n squared numbers and n squared numbers. So the actual input is 2n squared numbers. All right. That's the dimension. If you want to look at it that way, it's first of all you ignore constant factors. Second of all, this is only a square value. It's a polynomial factor of the input that we're going to really consider. The input will be 2 matrices, but the size, we can simplify that and just say n. So from that perspective, this is going to end up being a cubic algorithm. If you want to look at it from this perspective, then it's going to be an algorithm that is order n to the 1.5, and that looks kind of icky. Kind of the same way that pi is 3.14, that in a circle, it's 2 pi radians because it makes a whole bunch of other formula very, very simplified. If you had only 1 radian in a circle, 1 unit radian in a circle, then you've got all these extra, you have to write down all these extra things in a bunch of other formulas. So we're going to keep it simple and just say that our input size is n. Okay? All right. Well, just as this trick over here, you might ask yourself, how did Karatsuba come up with this? Well, first of all, it was known. I mean, it's just very simple algebra. It was known for a long time. Oh, yeah, you can manipulate it like this. How did you find out something like that? Well, you just sit there and you write down a bunch of things and equivalences, and well, I can factor that out, and I can factor that in, and I can take that value and reuse it down here, and you manipulate things, and then you find a way that it works so that you only have 1, 2, 3 multiplications. Well, a guy named Strawson came along and did the same thing with matrix multiplication. Strawson observed that you can actually split up a matrix multiplication. He wrote everything down, and he came up with the fact that if I've got a matrix that has entries A naught naught, A naught 1, A 1 naught, and A 1 1, right, times a matrix with B naught naught, B naught 1, B 1 0, B 1 1. Right? Well, normally if you just write everything out, then that's going to require that n cubed multiplications. But what you can actually do is you can establish 7 other values that he came up with and derived, so that you can do it something like this: m1 plus m4 minus, and don't worry, I will define these here in a second, m7, m2 plus m4, m3, for the upper right entry here, it's going to be m5, m1 plus m3 minus m2 plus m6. So you can see here that some of these things are reused. For example, m1 is used twice, m3 is used twice, m4 is used twice, m6 is only used once, as is m7. M5 here is used twice. So you've got a lot of repetition here. That once you've computed those smaller values, then you can go ahead and reuse them. M1 is simply just A naught naught plus A 1 1 times b naught naught plus b11. In other words, 1 multiplication. Right? And 2 additions. In fact, let me rewrite it like this. Let's go ahead and keep a running total here. So there's M1, multiplications and additions. 1, and then there are 2 of them here. Again, 1 and 2. All right. M2 is going to end up being A10 plus A11 times B naught naught. Right? So 1 multiplication and 1 additional addition. M3, M4, M5, M6, and M7. A naught naught times B naught 1 minus B11. So 1 multiplication and yes, 1 addition. Yes, this is a subtraction here, but a subtraction is just an addition by a negative number. So that's why we're counting it as an addition. M4 here is A11 times B10 minus B00. Same there, 1 and 1. M5, A naught naught plus A naught 1 times B11. And you'll immediately wonder here, why am I writing it like, why did I write it so that the scalar value was on the left here and the scalar value was on the right here? Remember, these are ultimately going to be matrix multiplications, and matrix multiplication is not necessarily commutative. Commutativity is that A times B is equal to B times A. That's not necessarily true, and that's not necessarily the case when you're multiplying matrices together. It is true when you are multiplying, say, scalar integer values together, but it's not true necessarily with matrix multiplications. A10, A00 times B00, B01. So 2 additional adds, 1 multiplication here. And then A01, A11. If I've made a mistake in transcribing these, it doesn't matter. Who cares? You can always go to the notes and get the full correct one. I'm pretty sure it's correct. All right. So how many total? That's 7 multiplications total down here. And then 2, 4, 6, 8, 10 additions. Right? But you also have to be aware that you are also performing additions over here. 1, 2, 3, 4, 5, 6, 7, 8. So 8 additions over here, and that's 18 total. So to multiply 2 by 2 matrices via Strassen requires 7 multiplications and 18 additions. Now, put on your memory cap here, and let's go back to this 2 by 2 example here. How many multiplications did we end up doing? We ended up doing 8 multiplications, right? 1, 2, to get the first entry here. 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. And only 1, 2, 3, 4 additions, right? So versus 8 multiplications and 7 additions. 7 was it? Sorry, 4. What did I just say? 4 additions for the naive way of doing this. Now you might say to yourself, well, you're only picking up 1 multiplication. You've reduced the number of multiplications from 8 to 7. But you've blown up the number of additions. You've gone from 4 additions up to 18 additions. Granted, yes. If I were analyzing this with respect to additions, that would be concerning initially. Ultimately, if you do analyze this with respect to additions, asymptotically, it's going to end up being the same. But multiplications are far more expensive than are additions, right? Still no questions? Okay. And no questions? Again, if you have questions, post to Piazza, please. Anyway, cutting down from 8 multiplications down to 7 multiplications actually turns out to be an asymptotic advantage. All right. Again, let's set up the number of multiplications. We're going to set up a recurrence relation here. Number of multiplications by Strawson. And again, we're going to end up ignoring all these additions because we're only capturing multiplications. The number of multiplications by Strawson on two n by n matrices. Right? These identities will work equally well on matrices of any size. Right? If I consider this, instead of 4 numbers, I consider these as 4 quadrants. And before they were n elements and n elements total, then each one of these things is going to end up being an n divided by 2 by an n divided by 2 matrix. Right? So I'm cutting it in half each and every single time. And then handing it off to a recursive call 1, 2, 3, 4, 5, 6, 7 recursive calls. So I can set up my recurrence exactly like that. 7 recursive calls to Strawson on inputs of size roughly 1/2. What happens when it's not a perfect power of 2? That's just a detail that you can hammer out. Basically, all you need to do is, if you really want to make it into a power of 2, you can go ahead and take your small non-power of 2 matrix and you can pad it out with zeros above and below and off the diagonal there. And then continue. All those zeros will never contribute anything to the multiplication. You will end up with a matrix where there are a bunch of zeros in the same places that you padded it out, and then you can take those zeros out and you've got the same matrix as before. Right? How many non-recursive multiplications do we do? 0. Right? We're only doing multiplications in the recursion. The base case, of course, you'd have to consider, when you get down to a 1-by-1 matrix, you've got a number. When you've got a number, it's just one multiplication. Right? Here's one number, multiply those two things together. You can use Karatsuba multiplication after that if you really want to. Right? But otherwise, that goes away. Right? Now, by the Master Theorem, I've got that A is 7, B is 2, and just like Karatsuba multiplication, there's no recursive cost, so D ends up being 0 here. 7 versus 2 to the 0, 7 is greater. So case 3 applies, the exact same case as we used before with Karatsuba multiplication, and the number of multiplications that Strawson ends up doing is going to be order n to the log base 2 of 7, which is roughly order n to the 2 point, I'm going to have to look that up, or I'm going to have to pull out Wolfram Alpha, 2.807. Right? Remember that the naive way of doing it, we have order n cubed. Strawson has improved that to slightly less than n cubed, 2.807. Doesn't seem like a big... so same points that I made with Karatsuba before apply here. It really only works with very, very large matrices. If you are doing very, very large matrices, then there are better heuristic ways of going about it. If they're dense matrices, then you can use different algorithms. If they're sparse matrices, then you can use different algorithms. But there are that you can parallelize it. There are lots of things that you can do in practice before you rely on some algorithm like this. Because again, you're splitting these things up into 2 matrices into 8 matrices. You will have a huge blow up in the number of additions in practice. Again, analysis here would lead you to the fact that it's actually going to be the same number of additions as multiplications asymptotically, n to the 2.8 something, right? But in practice, that blow up there is going to matter. You pay for the recursion. You pay for padding of the matrices to get it nice. You pay for a lot of stuff that is not captured by this big O analysis right here. So in practice, you would not use something like this. But there are other theoretical algorithms that are of interest. For example, the Vinogard method. Using just different identities, he was able to come up with one that was, n to the 2.375, right? The theoretically best, you have to look at all the input, right? So if you ignore an entry in the matrix, you're not going to be able to get the exact solution. So the theoretical best would be order n squared. So we've made, n cubed down to 2.8 down to 2.3. That's progress towards the theoretical best lower bound, right? And then, in fact, I think the vinyl guard method was improved. The analysis was improved now almost 10 years ago to order n 2.3727. And that was considered actually a huge, not breakthrough, but that was considered very, very interesting, even though it was only taking it down. It was the same exact algorithm, just a much better analysis. And it took it down to, like 2 or 3 1,000ths less, right? And so there's still this huge gap here, right? That we don't know how to achieve that best result there. But again, all of these are of very theoretical interest. In practice, this is not something that you'd actually want to do. In previous years, I have had people implement Strawson's matrix multiplication and even time it. Strawson's versus just a built-in one, and Strawson's has never performed better than the built-in one, even on very billions of sized matrices or something that's observable. You have to get very, very large in order for this to have any meaningful impact. All right. So there are no questions. Good luck on the remainder of your homework. I will be available from 1 to 2 like I am every day. Again, it was fixed and updated so that it is due at midnight, which is the intention. Sarah will be along at 3 o'clock. And hopefully you've got a good chunk of it done. You just need that one little tweak and it'll all be done. But otherwise, once that's done, start on homework 2 immediately. All right. Have a good day.